Okay, so yeah, this is two lectures in a row. The first one is about raster image correlation spectroscopy, or RICS. And then the second one is about number and brightness, or NNB. So what is the general idea of RICS? The idea of RICS is to measure, to quantify the motion of biomolecules, fluorescently labeled biomolecules, in live cells and even tissues. So some of the advantages of RICS is that it can be done on a commercial laser scanning microscope, which can be a 1 or 2 photon system, in addition, of course, to some home-built instruments. It uses a photomultiplier detector or an avalanche photodiode, so it can work in analog detection mode as well as in photon counting mode. Raster image correlation spectroscopy can provide an intrinsic method to separate out the immobile fraction, which is especially important for measurement in cells. And you can apply it to measure diffusion coefficients, to measure and distinguish binding, to measure active transport or transient trapping, or those kinds of processes. So how does it work? So in a laser scanning instrument, you acquire an image by focusing your laser beam into a single spot. And in that spot, you excite your fluorescent molecules. And then you detect the fluorescent from that spot with a single point detector, like a photomultiplier tube or an avalanche photodiode, which are most commonly used in those instruments. And yeah, in this, you just get the signal from a single spot. So in order to get a 2-dimensional image, you need to scan your sample pixel by pixel and line by line, which you can do either by moving the sample itself or by moving the laser beam, for example, with galvo mirrors. The latter is preferred for RICS because, as you will see later, you need to have, depending on how fast your molecules of interest move, you have to have a certain speed that you're scanning the image with. So here's just an illustration of the scanning process. So we start at some origin, and then we scan a line, raster it pixel by pixel. Then the laser jumps back again to the origin, and not the origin, to the left, but one line down, and then we scan the next line, and so on and so forth, to in the end get one full image. And then we go back to the origin to scan the next image of the same region of interest. So what raster image correlation spectroscopy is exploiting is that because we are scanning the image, which takes time, this image contains an intrinsic time structures. So one pixel recorded at the top left corner, for example, is recorded at a different time than another pixel at the top right corner, and so on. And because we set these parameters for scanning, we set the pixel dwell time, we set the line dwell time, we set how large the pixels are. We know exactly these parameters, and then we can use them to learn something about the movement of molecules. So typically, yeah, we have a couple of parameters. One is the pixel dwell time, and we have the line time, which is how many pixels are in a line times the pixel dwell time. But then you have to consider that you also have to jump back to the origin, to the left-hand side of the image to scan the next line. So you have this retracing time on top of it. And here on the right, you can see an example of such a laser scanned image, which shows a part of a cell expressing a fluorescent protein. Okay, so how can we get some information about the movement of molecules? Well, consider that you start scanning your image. Consider this the red point here on the left corner of the screen. Let me change this to pointer. Okay, here we go. And let's consider we also have a molecule in that spot at the time we start scanning. So now if we have slow diffusion, the molecule is able to follow or move the same way as the laser beam. There's a statistical chance for this happening. But the laser beam scans at a constant velocity, whereas the diffusion only goes with the square root in case of free diffusion. So if it's slow, at some point the laser beam will always overtake the molecule. So we may get a signal in the second pixel and maybe the third, but not pixel number 4 and so on from the same molecule. So if we calculate the spatial correlation for this kind of scenario, we are starting with a high probability to find the same molecule again in a neighboring pixel. But then it declines, and it declines rapidly because the laser moves away pretty fast and there's less and less chance to find that same molecule at a pixel further away. So now consider the same situation, but now assuming that the molecule can diffuse fast. So now there's a chance that we not only find the molecule in pixels, say 2 and 3, but also 4, 5, 6, and 7. So how does the spatial correlation in this case look like? This is represented by the red curve here. So again, we start with a certain probability to find the same molecule, and then it continues. So even at later pixel, it's not 0 yet because the molecule is fast enough to follow the laser beam. Of course, you have to take into account that this is a statistical method. For example, in the case of free diffusion, there's no reason that the molecule shouldn't go in the opposite direction as the laser beam. And of course that happens, but we are considering many molecules. So as an average, there is a certain probability that it will go the same direction as the laser. So how do we calculate the spatial correlation? Well, what we are considering is the probability for a molecule to move a certain distance. So this distance can be, for example, just 1 pixel distance from left, right, and right, left. And we are typically doing this analysis in a whole region of interest. So an area of a number of several numbers of pixels. So we repeat this calculation for all pixel distances of 1 for this small sub-image. And this will give us the average time it takes a molecule to move from 1 pixel to the next. And then we are doing the same operation for 2 pixel distance, 3 pixel distance, and so on for the whole image or sub-image. Then we are doing all the line combinations. What is the chance for a molecule to move from one line to the next? And then, of course, the combination of pixel and lines. So how does this look like mathematically? So we have our image, and now we correlate this basically with itself, but at a certain pixel and line shift. So we shift the image by 1 pixel, for example, multiplied with itself, then shift it by 2, again, do the same operation, again, do it for all lines, and do this operation for all shifts in X and Y direction. And then the number that we get for each pixel delay is normalized by the average intensity squared. So this is the basic autocorrelation function principle. Okay, so if we do this for 1 frame, we get our 2-dimensional spatial correlation function, which will show how to analyze in terms of interpreting it for any movement of molecules. But just a note here, typically just collecting 1 frame is not enough for signal-to-noise reasons. Because in cells, if you are dealing with, for example, fluorescent proteins, they're not that bright. So what we typically do is acquire a series of frames in the same plane. So maybe 50 or 100 or maybe even 200 frames, depending on the signal to noise level. And then we calculate the spatial correlation for each of them and then take the average. Taking more than one frame also has other advantages. For example, we can, to a certain extent, correct for bleaching and also subtract the immobile fraction, which I'll talk about in a minute. Okay, so let's recap. So in the raster scanned image, points are measured at different positions and at different times also. If we consider the pixel sequence, it's continuous. If we consider the time sequence, it's not continuous because, as you know, we're scanning one line and jump back, scanning on the line, jump back, and so on. Okay, so we now have to calculate the correlation function, which, because it's an image, a 2D system, is also in 2 dimensions. But if you look at the formula for single point FCS, it will look very familiar. So we have the intensity at a certain location, XY, multiplied with the intensity at XY, but plus a certain pixel shift and plus a certain line shift. Multiply, take the average, and then divide by the intensity squared. And we can set it down to 0 by subtracting 1. So the important variables are xi and psi, which represent the spatial increments in x and y directions. So how much pixel shift and how much line shift we're taking into consideration. So as we have seen before, it's quite a lot of calculations. You have to do this for all pixel shifts, for all line shifts. So you may think, oh, maybe this will take a long time. But you can calculate this very efficiently, actually, using fast Fourier transform algorithms. So a typical image series of 100 frames and 256 by 256 on modern computers, the calculation is almost instantaneous, only a few seconds or sub-seconds. Okay, so now in the to get the information out, we have to account for the relationship between time and position of the laser scanning beam. So what does this autocorrelation RICS function depend on? Well, we have a scanning term, which is called S here, which accounts for the motion of the laser beam. And then we have the other term called G here, which accounts for the motion of the molecules. So in the following, we'll just consider free diffusion, but you can have other models for active transport or trapping of particles. So anyway, for free diffusion, the probability to find a molecule can be described by this formula here, which essentially is exponential decay. So what this function here is representing in the 2 dimension is the probability to find a molecule at a certain location. If the molecule didn't have much time to move, then you will most likely find it near the center again. So then the peak will be sharp with a high amplitude. But as the molecules are able to move away, to diffuse, you can find them further away. So the probability will increase towards the periphery and decrease from the center. Yeah. And if you have fast diffusion, this process will happen fast as a function of time. If you have slower diffusion, this decay will happen more slowly. So this width of the Gaussian function will increase as a function of time. Okay, so how, in further detail, how does the autocorrelation function look like? Again, it looks very similar to the single point FCS function. So we have this correction factor gamma, which takes into account the shape of your observation volume. If you do single photon excitation, you can assume it's a Gaussian. So this will be 0.35. Then we have divided by the average number of molecules that we have. So you could also measure the concentration of molecules, just as in single point FCS using RICS. And then we have these terms here, which incorporate the diffusion coefficient in the case of free diffusion. Then we have tau p, which is the pixel dwell time. Then c, which is the current pixel shift that we are considering. Then we have the same for the line dwell time and line shift. And then we divide by the size of the observation volume squared, the size of the observation volume in xy squared. And then we have a second term, which has the same parameters, but then is divided by the point spread function extension in the axial direction and the z direction. So this accounts for the motion of the molecules, but then we also have an exponential decay here, which accounts for the motion of the laser beam. Okay, on the right-hand side, you see the illustration again that you have seen on the previous slide. So for slow diffusion, we expect this kind of bell-shaped curve, which decays rapidly. If you have faster diffusing molecules, the spatial correlation will extend further because the molecules were able to move to pixels that are further away. Okay. We also have to consider the pixel size, which is incorporated in this parameter delta R. And we can consider, well, what will happen, for example, if we have molecules, but they are not moving at all? How does this look like? Well, in that case, we will get just the average shape of the point spec function if we have particles that are smaller than the point spec function. If they are larger, we will actually get the shape, the average shape of the particle. And then if the molecules now can move, this will lead to a deformation in this correlation function, which is illustrated on the next slide. So here we have some molecules, for example, membrane proteins. Just wanted to, oh, here we go. Okay, so here this is simulated a very slow diffusion, 0.1 micrometer square per second, which, for example, could be membrane proteins. And if we raster scan an image, we just see those molecules, and then the 2D correlation function will look pretty much symmetrical. On the right-hand side is just a pseudo 3D illustration of the shape of the function in the center. Okay, now let's go a bit faster. So the next row is a simulation of diffusing molecules at 5 micrometers square per second, which, for example, could be beads in an aqueous solution. And now you can already see that there is some distortion in the image. And this is because you're scanning the image line by line, but at the same time, the particles were able to move to a different location. That is why you get this distortion in the pattern. If we calculate the correlation function, you will see this. It will manifest itself as a compression of the function between lines and an elongation between pixels. So the reason this is happening is now that the molecules can move, you have a higher probability to find them in pixels further away while you're scanning the line. But at the same time, because it takes quite long to complete the scan of the entire line and go back to the next line, the molecule most likely is already gone by the time you arrive at the next line, and this is why you have a compression in the y direction of the function. Okay, now let's go to something really fast, which is the diffusion of, for example, green fluorescent protein in aqueous solution, which at room temperature is about 90 micrometers square per second. Now, if you look at the scanned image, if I didn't tell you what it is, you would just say, oh, it seems like some kind of random noise. But now the reason is you have these stripes is that you are able to follow the motion of the molecule in one line, but then once you arrive at the next line, it's already gone. And this is exactly what you see in the correlation function. You see the strong compression in y direction and then a strong elongation on the pixel in x direction in this case. Okay, here's the similar thing illustrated for the pixel delay and line delay separately in two separate graphs. So again, this is a simulation of fluorescent particles simulated to move in an image of 128 by 128 pixels. We simulate to scan with a time of 8 microseconds per pixel, and the pixel size was set to 30 nanometer. And then the different colors represent the analysis of simulating different diffusion coefficients. So the black one is 100 micrometers square per second. And for the pixel to pixel correlation, you see you have this initially faster decay, but then you have the further extension of the tail. Again, this is because molecules are now able to move and you're likely to find them at a larger distance. Then for 10, this goes down. You have more this classical Gaussian shape. And you see that between 10, 1, and 0.1 for these settings, there's not that much difference anymore in the pixel-to-pixel correlation. So the pixel-to-pixel correlation is more sensitive for a faster time scale. If you look at the line-to-line correlation, you see for the very fast diffusion, for 100 micrometers square per second, the black dots, you almost get no line-to-line correlation. But then it increases and you have a stronger difference for the slower diffusion. So the line-to-line correlation is more sensitive for the slow processes. So this is kind of nice because you are having it as a 2D system. You're exploring two different time scales, the microsecond time scale typically for the pixel to pixel and the millisecond time scale typically for the line to line. So you have access to a broader suitable range to get the diffusion coefficients of molecules. Okay, so what parameters should you use to set up your laser scanning microscope? Depends a bit on how fast the molecules of interest are moving. Of course, now this is what you want to measure. So maybe we don't know in the beginning what the range is. I mean, you can have some general ideas. If it's in the membrane, it will probably be slower than in the cytoplasm. But if you're absolutely not sure, you can just do multiple tests at multiple pixel dwell times and see at which speed you're getting something. So for fast diffusing molecules like dye in solution, for example, faster than 100 micrometers square per second, you use 4 microseconds, and faster as pixel dwell time than 8 to 32 microseconds for slower molecules in the range of 1 to 100 micrometers square per second, which is the typical range for the motion of protein in the cell cytoplasm, and then 32 to 100 microseconds for slower molecules, 0.1 micrometer square and higher, which is more in the range of a membrane protein, for example. Okay, the next parameter you have to consider is the pixel size. So what we need to do is we need to set up the instrument that the size of individual pixel is about 3 to 4 or 5 times smaller than the size of the point spread function of your instrument. If you're using a high numerical aperture lens, which you should in this case to get as many photons as you can, the size of that point breadth function will be in the range of maybe 250 to 300 nanometer. For example, for a numerical aperture 1.2 water immersion lens is one that we typically use for those kinds of experiments. And the reason you need to set up your pixel size smaller than the point spread function is that you need to sample the curves. So you need a couple of points to be able to fit the data. If all the data is compressed in one point, you cannot do any quantification of your data. For the molecular concentrations, it's similar to conventional FCS methods like single point FCS. Typically, these methods work well at the nanomolar range, like 100 picomolar maybe to 10 or 100 nanomolar. But it depends on the signal to noise behavior of your system, the brightness of your molecules, but that's kind of the general range. So here's illustrated what happens if the parameters you set do not match the motion of the molecules. So the first example on the top, the scanning speed was set too slow. So this 100 microsecond dwell time per pixel was used to measure the diffusion coefficient of a dye of 300 micrometers per second. And you can see that it extends, you have a very long tail because the dye moves faster, much faster than the laser beam, so you're not able to capture the full decay. So your data set is kind of truncated, which will give you a problem in the fit. The other example on the bottom row is here that, as just mentioned, the pixel size should be smaller than the point spread function size. If you're not doing that, for example, here the pixel size was set equal to the point spread function size, then your data gets all compressed into a few pixels and you no longer be able to accurately get the information of the diffusion coefficient from the shape of this function that you are trying to fit. Okay, let's look at some examples. This was a solution of eGFP. So you see a single image of that solution. The acquisition was set to 128 by 128 pixel, 4 microseconds per pixel, which in this case resulted in a line dwell time of 5.4 milliseconds. And the pixel size was set to 23 nanometer, which oversamples the point spread function. So this is the resulting spatial autocorrelation function. And then if we are fitting the model for free diffusion to it, which you have seen on the previous slide, in this case, we got about 100 micrometers squared per second, which corresponds well to the expected diffusion constant of eGFP in solution. Okay, so let's explore this a little bit further using different data analysis settings. So in this case, a total of 500 frames were collected, but only on the top row, different fractions of those number of frames were analyzed and different regions of interest were used. And the top row is for the correlation amplitude and the bottom row is for the diffusion coefficient. So let's look at the correlation amplitude first. So we see the bars on the leftmost, which says 256. So here we took the full image of 256 by 256 pixel and analyzed different numbers of frames. And you can see that you pretty much get the same amplitude independent, more or less, how many frames you were taking into account. Then a smaller region of interest was analyzed, only a quarter, 128 pixels. You see you still get a pretty much reliable results, even as you reduce the number of frames you include in the analysis. but you already can see that the error increases the less frames you are using. Further reducing to 64 pixel, again, the error increases, and then 32 pixel, you see that, well, at 1 frame, the result becomes kind of unreliable. But still, it's pretty much consistent, so the amplitude seems not to be too sensitive to these variations. Now let's look at the diffusion coefficient. So again, we have different sizes of the regions of interest, 256 down to 32 by 32 in these color-coded bars. And then on the x-axis, in this case, we have the number of frames analyzed. So 100 frames, you analyze 256 by 256, 128 by 128, you get the same result. Then 64 by 64, you almost get the same result, but then 32 by 32, you underestimate the diffusion coefficient significantly. And this trend continues the less frames you analyze, but of course, the less frames you analyze, also the other results with the larger region of interest have a larger error. But you can see that with the small region of interest, you systematically underestimated the diffusion constant. And the reason is now, because you have fewer pixels, you're not capturing the full decay anymore. So then basically in the fitting, there's a part of the function that's missing, and that is what is leading to this underestimation of the diffusion coefficient. Now, this was an example of eGFP, which is diffusing rather fast. So in this case, because it's diffusing rather fast, you need a relatively large region of interest to analyze to be able to capture the movement of the molecule. If you would have something that moves slower, you could potentially analyze smaller regions of interest because the molecules were not able to move that far. So you're still able to capture the decay in, let's say, a region of maybe 16 by 16, if your molecules are sufficiently slow and you have sufficient signal to noise. Okay, so yeah, RICS analysis in general can give you those two parameters. One is the average number of molecules in the observation volume, which you can convert to a concentration once you know the size of your point spread function. The other one was the motion parameter, which can be a diffusion constant in the case of free diffusion. So let's look at the concentration measurement via RICS. So this was a solution of fluorescein in a buffer. And as a reference, an absorption measurement was taken to calculate the concentration of the solution, and then a RICS measurements were taken of the same dilutions. And as you can see, you get a nice correspondence, a nice linear scaling as you would expect. So you can also quantify concentrations using the RICS methods. Okay, so far what you have seen were all either simulations or measurements of fluorescent proteins or dyes in solution. So what happens in cells, which is the interesting part? So in cells, we have some other things to consider. For example, cells can have an immobile fraction. So you can have some molecules that give you fluorescent signal that don't move. They are just sitting in the same place, more or less. And then you have other molecules that will also contribute to your fluorescent signal that are actually moving. And these are the ones that you are interested in measuring. So we have typically this immobile fraction in cells, and we need some way to correct for that. Because otherwise, these spatial features of the cell will give you a strong correlation pattern that overshadows the pattern from the motion of the molecules that you actually want to measure. So how can we separate out this immobile fraction before doing the calculation? Well, first, a few considerations. So if there's a truly immobile bright region, the intensity fluctuates according to the Poisson distribution due to shot noise. You just have molecules that are sitting there, you excite them, they emit photons, which are single particles, and so you can assume a Poissonian distribution. And so the time correlation of the shot noise is, the time correlation of shot noise is actually 0, with the only exception of the 0 time point. So actually, we always have to include the point of 0 pixel delay. So we can only analyze the non-zero pixel and line delays. So the spatial correlation of the intensity at any 2 pixels due to shot noise is 0, even if the 2 points are within the point split function. So that's a positive. So we actually should not get correlation just from that. So the idea is, if we subtract the average intensity and disregard the 0 point, the immobile fraction should disappear from the correlation function. There's only one small caveat, which is you have to be careful for analog detection, because there can be a correlation in the noise actually. So in the analysis, you may have to jump a couple of pixels to avoid this detector correlation. Okay, so how does the calculation work? So we record a series of images in the same plane, maybe 100 images, and then we take the average of this time stack of images. So for each pixel, we calculate the average fluorescence intensity collected in that point. Then from each individual image, which here is called I with subindex I, we subtract this average, which represents the immobile fraction that always has the same intensity because it doesn't move. However, this calculation can yield negative values, because now in each frame you can have more or less signal, whereas the average is this constant value of this in this pixel. So what we need to do is we need to add back in a value, and we can just take the global intensity of the entire image stack and add that back in. That will so basically introducing an offset, which will not at all change our correlation function. So down here on the right is the formula that you have. So we subtract the immobile fraction by taking the average of all image frames that we collected. Then for each image frame, we subtract this average in each pixel, and then we add a constant, which we typically set to the global average of all frames and all pixels. And then this image stack, which is now corrected with the immobile fraction subtracted, can then be subjected to the RICS analysis. So on the top right, you have this illustrated on the in those 3 panels. On the left-hand side, the immobile fraction subtraction was not performed. So you see a very strong correlation pattern corresponding to the average shape of the cell, which you see on the left here. Then the middle represents the average of those images taken of the cell. And if that is subtracted before, we end up with the correlation function seen on the right, which now only contains the contribution of the molecules that are actually moving around within the cell. So this is one reason why it's in RICS good to take more than one image, because we're able to do to subtract the immobile fraction. Another issue that can happen in cells is photobleaching. So while you're acquiring the image, you're illuminating your molecules, and they can eventually photobleach. And this results in an overall reduction in the fluorescent signal. So again, if we do this average subtraction, we can kind of correct for that. So how does that work? Well, instead of taking just the average of the entire image stack, so average frames 1 to 100 and subtract that, we split it up. We calculate, for example, the average only between frames 1 to 10. And then we subtract that from, let's say, frame 5. And then for frame 6, we would subtract the average between frames 2 and 11. And from 7 between 3 and 13, and so on and so forth. So by doing this average subtraction in kind of a moving average, rolling average fashion, we can correct for the bleaching as we subtract less and less as we get less and less signal. Yeah, so this is another very nice advantage of the method, that you can correct for bleaching as long as it's not too severe. I mean, if you bleach down to 0, of course, there's no more signal left for you to analyze. So it can work to a certain extent. Okay, here's some example of the removal of immobile structures or also slow-moving structures, which can also appear in cells. So these are focal adhesions, and RICS was analyzed in this region marked by the red square. Here you see the zoomed-in image, and then this was calculation of the spatial autocorrelation function without removal of the immobile fraction. But then when the immobile fraction is removed, here you see the adhesions disappear because at least in this current state, there was no dynamics going on. And what we were left with was only the autocorrelation functions of the molecules that are moving around those focal adhesions. And then fitting this using the diffusion equation and entering the parameters, pixel size, pixel time, line time, and size of point space function that were used in this acquisition, we get that in this region, there were 2 components for diffusion, one component diffusing at 7 micrometers square per second, and another slower component at 0.5 micrometers square per second. So let's look at a few examples to further illustrate the raster image correlation spectroscopy. The following examples look at cell migration, which is an important biological process in many responses. And the cell forms these adhesion complexes that it can grab onto extracellular structures. And there are many molecules involved in formation, assembly, disassembly of these adhesions, connecting with the outside, connecting with the inside of the cell across the cell membrane. And one of those molecules involved is called penicillin. And this was fluorescently tagged by using fusion construct where the DNA for penicillin was fused to the DNA encoding for the green fluorescent protein and then expressed in CHOK1 cells. So this is, you see a typical image acquired in the laser scanning microscope. And those bright spots are the focal adhesions near the glass where the cell connects to the coating of the glass, which in this case, I believe was fibronectin. Okay, so now in the acquisition, the number of frames, so 100 frames or so were required. And then you can calculate the diffusion coefficient in regions of interest. So in subregions, for example, 32 by 32 pixels. So if you do that in the cell cytoplasm, you get that the penicillin EGFP fusion is diffusing in this case at about 10 micrometers square per second, which is quite fast. But then if you shift your attention to other regions near focal adhesions, you see there the Paxillin EGFP is moving much slower, 10 times slower, about 1 micrometers per second. And you can even find other regions where it's down to less than 1 micrometers per second. And here's an example of how to kind of create a diffusion map. So you define a size of your region of interest, again, maybe 32 by 32 pixel. You calculate the diffusion coefficient based on the RICS analysis in that region. Then you shift the box, calculate again, and then get a map in this fashion, the entire image. So in the panel in the middle, you see the result for the correlation amplitude, which is inversely proportional to the number of molecules that were detected. And then on the right-hand side, you see a map of the diffusion coefficient. And you can see this heterogeneity where more towards the center, you have faster diffusion of the Paxillin in the cytoplasm. And then near the adhesion, where the Paxillin molecules cluster together and then bind to the, or are incorporated into the adhesion complex, then the diffusion is slowed down. Okay, but for these maps, one limitation is that the spatial resolution of those maps is limited because the resolution of the microscope is limited to begin with.
Can you hear me?
If the resolution of the microscope is, say, 300 nanometer, then the resolution of the diffusion coefficient map is not 300 nanometer because you need to add it within a region of a certain number of pixels. So the effective spatial resolution of your diffusion map is maybe on the order of a couple of micrometer.
Nick, can you hear me?
Yes.
We are more or less on time. I don't know how much is left because we are on the 45-minute more or less ready.
Mm-hmm. I can, I mean, I have this part about the super resolution and then the number and brightness will be shorter.
Okay, continue, go ahead.
Okay, thank you. So back to the resolution limits. So typical optical resolution with a high numerical aperture objective lens in X direction is on the order of maybe 200 nanometers, and in Z direction is maybe on the order of 500 nanometers. So this limit has been overcome. There are several approaches. One of them is stimulated emission depletion, which relies on switching the fluorophores, optically switching the fluorophores between a dark state and a bright state. And how this is switched is using by the principle of stimulated emission. So if you consider a fluorescent molecule, if you hit it with a photon in the excitation spectral range, you can transfer it from the electronic ground state to the first excited state. And then to go back to the ground state, it can spontaneously emit a fluorescence photon. Because you have vibrational decay and relaxation of the molecule, this spontaneous emission is typically redshifted with respect to the excitation spectrum. Now, alternatively, what you can do, if while the molecule is in the excited state, if you hit it with a photon that's within the emission range, you can induce the release of the fluorescence photon, which then is called stimulated emission. Otherwise, you just have to wait, and after some time, which is the fluorescence lifetime, it will go back to the ground state. So STAT microscope leverages this principle by overlaying the excitation spot with the depletion pattern in the form of a donut, which has zero intensity in the center. So what is effectively happening is you excite molecules that are within your diffraction limited area. So let's say 300 nanometer. Then you hit it with the depletion beam. So you will induce the release of the photons on the periphery, but not in the center where the intensity of the depletion pattern is 0. So only the molecules in the center can spontaneously emit fluorescence, which is the one that you're detecting. And by increasing the intensity of the depletion beam, you can shrink down your effective observation volume. So this is illustrated here. You see a regular confocal microscope with an example image of fluorescent beads, and then once you apply the depletion beam, you can shrink down the effective point spec function and ends up with higher spatial resolution. This can be quantified by extending the equation for the resolution by this factor 1 over s, where s is the square root of the 1 plus this intensity of the stat beam divided by the saturation intensity of the molecules for depletion, which depends on the absorption cross-section and the lifetime of the molecules. And then here's just an example of increasing the stat power, and you increase the optical resolution. And here's an example image of microtubule labeled with a dye, and then on the left you have confocal, and on the right you have the subdiffraction stat image. So how does this apply to the raster image correlation spectroscopy? Well, now we have a way of shrinking the effective point spec function. So we can use smaller pixel size to scan. The other maybe advantage is that because we are probing a smaller volume, considering the same number of molecules, on average, we now have less inside the smaller volume, so the fluctuations will be larger, which will increase the correlation amplitude. Here's just an example of the lipid bilayer where we have lipids DPBE labeled with a far red dye R2647N, and you see the measured number of particles as a function of the area, where the area was controlled by increasing the stat power, and it scales. And the same you can see for the diffusion time, which is the average time it takes the molecule to cross the observation volume. And as we shrink the observation volume down, or the observation area in this case of the membrane, the transit time, of course, will be less. So going back to the cells, this is R2647N DPBE to label the plasma membrane of these XTC cells. Here is a confocal acquisition of the cell, and if we try to analyze very small regions using the RICS method, you see it's very noisy because we don't have enough spatial resolution. But once we apply the stat, you can see that it's possible to measure the diffusion of the molecules in smaller regions of interest. So to summarize, the RICS method is able to measure the motion of small molecules, cytosolic proteins, and also transmembrane proteins that diffuse a little bit slower. For very large protein aggregates moving very slowly, other methods may be preferred. So the typical time scale of observation for RICS is the pixel dwell time in microseconds and the line time in milliseconds. And you can use temporal image correlation methods, which do frame-to-frame correlation to access the slower processes on the minute time scale. Yeah, so temporal image correlation, the time resolution is second. You have a spatial resolution at the single pixel level, which is good for large aggregates. Then we have RICS on the microsecond to millisecond time scale, with a spatial resolution of the diffusion map of maybe 2 micron or so. And then you can improve upon the spatial resolution by applying stat.